Hey friends. Okay, long title, concavity, inflection points, and the second derivative test. This would be lesson 5 of optimization and curve sketching. Second last lesson, actually. Our last lesson in this unit is just putting all of this together in one question. So these are kind of the last bits and pieces that we have to deal with before I just kind of say, here's an equation, analyze it, and sketch it. Okay. Okay, so consider the following graph of f of x. In general, the graph of f of x is called, concave downward on the interval if f of x lies below its tangents on that interval. So just for example here, here's a tangent. Okay. The graph lies below. Here's a tangent. The graph lies below. Here's a tangent. The graph lies below. Okay, so all these tangents that I'm doing right now, the graph lies below. Here is a tangent. The graph lies above. Okay, so I concave down if the graph lies below the lines of tangent. I concave up if the graph lies above the lines of tangent, okay? Or the tangent lines of tangent. That doesn't sound right at all, does it? Okay, I just make stuff up. In the above example then, f of x is concave downward on the interval negative infinity to c. So this point right here, let me clear the drawings. This point right here would represent where I shift from concaving downward to concaving upward, okay? And that point is called point of inflection, which we'll get to in just a second, okay? Okay, so, or I concave upward on the interval if f of x lies above its tangents on that interval. So in this example, it would be from c to infinity, okay? Awesome. Okay, so if a curve changes concavity. So if I'm going from a moment where I concave down to a moment where I concave up, that's called, that point, c comma f of c, would be called a point of inflection. Okay. Okay, so sketch a curve of f of x equals 1/10 x plus 7, x plus 1, x minus 5. Okay, you can use your graphing calculator to help at this point of the game, but you know, you've got an x-intercept at -7, at -1, and at 5, okay? So the graph looks like this, and you probably have that all set to go in your graphing calculator. Okay, now, we want to draw the derivative of f of x and the second derivative of f of x, okay? So you should be comfortable right now in your mind's eye to actually have a picture of what both of those would look like, but go ahead and draw them in. Pause me for a second and then compare. Okay, so the derivative looks like the green guy here, and then the second derivative is my pink guy, okay? Now, what we want to do is we want to kind of analyze the second derivative for a moment, especially at the point of the inflection point where the concavity changes. And I want you to notice right away, take a look at this, the second derivative is 0 right at that point of inflection, okay? I think just based on the previous slide, you'd be comfortable to say visually there is a point of inflection there, right? That's kind of that midway point where I have to kind of change from drawing tangent lines above to drawing tangent lines below, okay? Okay. So the first and second derivatives indicate different things about the original function f of x. From your sketch, you should be able to conclude the following. Okay, so the first thing we're looking at is concavity. Now, quick note, the second derivative is the rate of change of the first derivative. That sentence should sound pretty comfortable to you at this stage of the game. So the graph of a twice differentiable function of y equals f of x is concave up when the second derivative is greater than 0. Look at this green portion. I'm just going to hide my big head for a sec. Look at this green portion that I have shaded on the graph. For that whole time, the pink, which is the second derivative, is positive. Okay, so when the second derivative is positive, on that interval, we should notice that there's a relative minimum there. Okay. Likewise, I'll be concaving down when the second derivative is less than 0. So on this blue section that I just shaded in, you'll notice that the pink line is always below the x-axis. It's always negative, okay? And that means when the second derivative is negative, on that interval, we should see a maximum point, okay? And we do right there, okay? So, to find possible points of inflection then, what we're essentially doing is we're looking for when the second derivative equals 0 or when the second derivative doesn't exist, okay? Now, that's just like what we were looking for when we were looking at the first derivative and finding critical numbers, okay? It's the exact same process. We're gonna put them on a number line, we're gonna test to the left and to the right, and if we see a change in positive to negative or negative to positive, we know we have a change in concavity, which means we have a point of inflection. Okay, so all of that's going to feel very, very familiar to you today. But we don't call them critical numbers if we're dealing with the second derivative. Okay, we only call them critical numbers if we are dealing with the first derivative. Okay, so the second derivative test is the following. This is also a test for relative extrema, which are max and mins, like the first derivative test. But this is not a test for concavity. Okay, in order to test for concavity, we actually have to go on either side of our numbers. So if the first derivative is 0, okay, well, that's a critical number if the first derivative equals 0. Okay, so the first derivative test would say, okay, now test left or right. Here we're saying, okay, well, sure, but if the first derivative is 0 and the second derivative is positive, we just talked about the fact that if the second derivative is positive, we would have a relative minimum there. So you know you're going to have a relative minimum if the second derivative is positive, okay? Or if the first derivative is 0 and the second derivative is negative, then you'll have a relative maximum there, okay? Now, just a quick note there, this test will not work if the second derivative, so f prime of c is 0 or does not exist. If this happens, you'd have to just use the first derivative test, okay? Okay, so the second derivative test is great for polynomials, but if you have a more complicated function, usually it's best to stay with the first derivative test, okay? So now we are going to start analyzing graphs, and this is going to feel very similar to where I left you off on the last lesson. The only difference is we're going to take it one step further now, and we're going to look at the second derivative, and we're going to set the second derivative equal to 0 or non-existent, and that's going to help us analyze when the graph concaves up, when the graph concaves down, and whether or not there's a point of inflection. So in the last lesson, you know, you had statements like it increases on this interval, it decreases on this interval, and there is local minimums here and local maximums here. Now to that, we're going to add to that list. We're still going to say all of that stuff, but we're going to add, sorry, I hesitated because there's a bunch of birds chirping in the background, and I don't know if you can actually hear that in the video or not. Sorry, so what we're going to add to that list is where the interval that the graph concaves up, the interval that the graph concaves down, and whether or not there's a point of inflection, okay? So summarizing before we get into that analysis that I just described, if the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. If the first derivative is 0, then the function has a possible max or min. Okay, all of those statements should sound pretty familiar at the current moment of your life. Then, if the second derivative is positive, the function will concave up. If the second derivative is negative, the function will concave down. And remember, if I concave up, I'm like this, so I would have a local minimum at some point. If I concave down, I'm like this, so I'd have a local maximum at some point. Okay, and then if the second derivative is 0, at that point I would have a possible point of inflection. Okay. Now, to test whether it's actually a point of inflection, I have to change concavity. So I would check on the left and on the right and see if it changes from negative to positive or positive to negative. Okay, cool. Okay, so here we go into analyzing things. Determine the relative extrema, concavity, and any inflection points for the following functions. Again, extrema is just max and mins. Okay, so I've given you f of x equals x cubed minus 3x plus 1. First thing you got to do is get me the first and second derivative. Okay, so first derivative, 3x squared minus 3. Second derivative, 6x. Okay, now, first thing we're going to look at is intervals of increasing and decreasing and local max and mins, just like we did yesterday. Okay, so I want to think, where does the first derivative equal 0, or where does the first derivative not exist? I can factor out a 3 from that 3x squared minus 3. That'd give me 3 times x squared minus 1, which would be x plus 1 and x minus 1. So I know that the first derivative, I've got critical numbers at -1 and 1. Okay, so I'm going to test those. I put a number line on, I mark where -1 is, I mark where 1 is, and then I'm going to test on each of those sections. So I need a number less than -1, I need a number in between -1 and 1, I need a number greater than 1. I'm plugging those numbers into the first derivative to see whether they're positive or negative. You're going to do that now. You can pause me for a sec. You should have ended up with positive, negative, positive. Okay, and now we're going to analyze what we just figured out. So I can now say that I'm increasing, this function is increasing from -infinity to -1 in union with 1 to infinity. I can say this function is decreasing from -1 to 1. I can say I'm going from positive to negative there, so I have a local max. So I have a local max at -1 comma something. I have to figure out my something, so I just plug -1 back into my original function to get the y value. And I can say that I have a local minimum at 1 comma something. Again, I'm going to plug that 1 back into my original y, or my original f of x. Okay, so I'm increasing from -1 to -infinity to -1 in union with 1 to infinity. I'm decreasing from -1 to 1. I have a relative max at -1 comma 3, and I have a relative min at 1 comma -1. Awesome. Really, I took you all the way up there yesterday, so none of this is new yet. Okay, now I'm going to I'm going to look at concavity and test for a possible point of inflection. Okay, so the possible point of inflection would occur when the second derivative equals 0, which would occur at x equals 0. So I'm going to plot 0 on a number line and check to the left and to the right. And when I do that, I get negative to the left and positive to the right. So now I have 3 more statements in my analysis I can make. I can say that I concave down from -infinity to 0. I concave up from 0 to infinity. And because I had a change in concavity at 0, because I went from negative to positive, that also tells me that I do have a point of inflection at 0 comma whatever the y value is. Again, remember, when you go to get that y value, you're plugging it back into the original. Sometimes you're plugging things into the original, sometimes you're plugging things into the first derivative, sometimes you're plugging things into the second derivative. You have to keep your head on straight as to what you're doing at any given moment, so you remember to use the right formula. So I have an inflection point at 0 comma 1. Okay, so this is a beautiful analysis of f of x equals x cubed minus 3x plus 1. Now I said that the last lesson we're going to do, not right now, but next time. Actually, I never said this yet, but this is going to be 2 days worth of lessons. So if you're freaking out about how fast this is going, you're going to have like a work period attached to this guy. But think about this for a sec. The last one is, okay, do all the analysis and then draw this. Well, if you think about this whole list of things, you're very solid on the point -1, 3, on the point 1, -1, on the point 0, 1. You know when you increase, you know when you kind of have to concave up and down, so you kind of know how your curves should look. You can actually draw a really accurate sketch of this graph now without the aid of graphing calculator, okay? But right now we're just kind of analyzing, so that'll be the last lesson that we do, is putting it all together and actually drawing a picture. Okay, so now we're going to try f of x equals x to the 4. So again, I need my first derivative, I need my second derivative. First derivative would be 4x cubed, second derivative would be 12x squared. And here I go. My critical numbers are when the first derivative equals 0 or when the first derivative doesn't exist. For this guy, that would be x equals 0. I'm going to plot that on a number line, test to the left and test to the right. I'm testing the first derivative right now. So when I plug in a negative number, I'm plugging it into the first derivative. That's going to get me negative on the left and positive on the right. So that tells me I am the original function is decreasing from -infinity to 0. I am increasing from 0 to infinity. And I have a local min at 0, 0. Okay. Now I'm going to test for a possible point of inflection. So I'm thinking, where does my second derivative equal 0? My second derivative equals 0 at 0. I'm going to plot that on a number line. Test to the left, test to the right. This time though, when I plug in a negative number, because that's to the left of 0, I actually get out positive. And when I plug in a positive number, I get out positive. So for this guy, there is no point of inflection. I concave up the whole time. Okay, so I'm concaving up from -infinity to infinity, and there is no inflection point. Make sense? Yeah, makes sense. Okay. Oh, this is fun. Okay, so you're going to figure out the first derivative. I will figure out, or I will tell you what the second derivative is, okay? Because the first derivative is a little bit of work. So go ahead, pause me for a sec, and then I'll walk you through my answer. Okay, so if I'm going to take the first derivative, I see the product rule here. So this is the derivative of f times g plus f times the derivative of g. So the derivative of f would be 2/3 x to the -1/3 times g plus f times the derivative of g. So I've got 1/3, 6 minus x, the 1/3 exponent drops down a degree, so that goes down to -2/3. And then the derivative of the inside function would be -1, okay? All right, now how can I clean this up? Well, I can factor out a few things. Okay, so the first thing I did was I just factored out 2/3 x to the negative, oh, no, sorry. First thing I did was just clean up a few things. So the -1, that's literally all I did in this slide. So that's a lot of writing, but I wanted to just clean it up for a sec. So the -1, I just kind of moved to the front, and then I put this as a coefficient in the first guy, okay? Okay, so the next step is to factor this. So what I'm going to do is I'm going to take out, sorry, I'm just trying to get my ink going here. I'm going to take out 6 minus x to the -2/3. Usually you want to take out the higher negative exponent, right? When I do that, oh, and I'm going to take out 2/3 x to the -1/3, okay? So when I do that, this term here, I'll be left with 6 minus x to the 1/3 over 6 minus x to the -2/3, which becomes 6 minus x to the 3/3, which is just 6 minus x, because that's to the 1, okay? The second term, 1/3 divided by 2/3 would be 1/2, and then my exponent will be 2/3 plus 1/3, which is 3/3, so it'll just be x. Okay, so sorry, I'm trying to get my ink cleared so that I can show you what I just said. Okay, so I took out the 2/3 x to the -1/3. and the 6 minus x to the negative 2/3. That left me with the first term being the 6 minus x right there. And then this term here left with the negative 1/2 and the x. Okay. Now I want to add these together. So negative 1/2 and negative 1/2, sorry, negative x and negative 1/2 x would be negative 3/2x. So I'd have negative 3/2x plus 6. Okay. Now this guy here, whoops, this guy here, x to the negative 1/3 will come to the bottom. So that'll be 2/3 cube root x. This will also come to the bottom. So that would be 1/the cube root of 6 minus x all squared. And then this is on the top right now. So I'd want to try and work with that a bit. So what I did on that guy is I just made a common denominator. I called that 6 12/2. So I had the whole thing as one denominator. Now I'm just going to put it all together. Okay, so this 3 could come out. So that could be 3 joins with that 2. And that would leave me with x plus 4. Actually, just to show you that for a second, if that 3 got factored out like that, then I'm just going to also cancel it with this 3 here. Okay, and then those 2's will actually divide each other out as well. Yeah, so that's going to leave me with negative x plus 4, and then the cube root of x times the cube root of 6 minus x all squared. Okay. Just for clarification, I'm just looking at my slide here. This negative sign here, I'm going to fix that in a second after the video, but that negative sign really shouldn't be on this whole fraction. It was only on the 3/2, right? So I should have really put that negative sign right there. I don't want you to think that that negative sign would have applied to the 4. It doesn't. It was only on that first term. Okay. Okay, cool beans. Let's get rid of all that ink. So there's the first derivative. I promised you that I would give you the second derivative. So there's the second derivative. Now I want you to take 10 minutes, or take as long as you want. You're gonna pause me. You try and do it as much as possible, okay? You try and do this whole analysis by yourself. I wanna know increasing, decreasing. I wanna know local mins. I wanna know local maxes. I wanna know where I concave up, where I concave down, and I wanna know any possible points of inflection. Okay, you try and write that all out and then come back to me, and we'll see how you did, okay? Okay, welcome back. Here is what the graph looks like. Okay, and now what I'm gonna do is I'm gonna walk you through each step as to all the information that we gathered that would have gotten us to this picture, okay? Just for your own knowledge, here's what the first and second derivative looks like. The first derivative here is green, and the second derivative is the pink guy, okay? So here we go. First thing I want to do is figure out the critical numbers. Well, the critical numbers are when the first derivative equals 0, or the first derivative doesn't exist. Those are going to be at 0, 4, and 6. It's going to be, I'm just going to hide myself for a sec. It's going to be 0 because it's a non-permissible value here. It was 6 because of the non-permissible value here. And it would have been 4 because that would have made a 0. Okay. So 0, 4, and 6. I'm going to plot those on a number line, and I'm going to test numbers in between so I figure out each range. At this stage, I'm testing those values into the first derivative to see whether they're positive or negative. That's going to give me negative, positive, negative, negative. Okay, so now I'm ready to talk about local maximins and intervals of increasing and decreasing. So I'm going to say I'm decreasing from negative infinity to 0 in union with 4 to 6 in union with 6 to infinity. I'm going to say that I'm increasing from 0 to 4. I'm going to say that I'm increasing to decreasing. So I have a local min at x equals 0. I got to figure out my y value. So I go back to my original function, plug 0 in for x, and figure out the corresponding y value. I have a local max at x equals 4. comma something, right? So I'm going to take that 4, go back to the original equation and plug in 4 to get my y value. So it's a relative min at 0, 0 and a relative max at 4 comma 2 to the 5 over 3. Okay, now I'm going to take a look at the second derivative, and I'm going to look at where does the second derivative equal 0 or where does it not exist, because those will be possible points of inflection. Remember, we're not calling them critical numbers when we're dealing with the second derivative. So those are at 0 and 6. Okay, and so I'm going to plot that on a number line. I'm going to test numbers for each section into the second derivative to see whether they're positive or negative. I end up with negative, negative, positive. So that means I'm going to concave down from negative infinity to 6. I'm going to concave up from 6 to infinity. And because I have a change of concavity or a change in concavity at 6, it means I have a point of inflection at 6 comma whatever my y value is back to the original function. So I have to plug 6 back into the original function and get out my y value. So I concave up from 6 to infinity, concave down, negative infinity to 6, and an inflection point at 6 comma 0. Now, remember I said that this was a 2-class thing. So this is where in-person class I would stop and you would just get going on your homework. I have one more example that I'm going to do with you right now, but in class I will start the next day with this example just to kind of use it as a refresher. Okay, so for this guy, again, same question, we're going to analyze the graph, but we're looking at x cubed minus 9x squared plus 15x minus 5. If you're at home working through this, why not just pause me and see how far you can get before you look at all my work. Okay, everything's easy when you watch someone else do it. Okay, so I'm going to find the first derivative and the second derivative. First derivative would be 3x squared minus 18x plus 15. Second derivative would be 6x minus 18. So I start looking for intervals of increasing and decreasing. I want to know when the first derivative is 0 or doesn't exist. So I got to factor that 3x squared minus 18x plus 15. I'll take a 3 out. That's going to leave me with x squared minus 6x plus 5. So then I'm looking for two numbers that multiply together to give me 5 and add together to give me negative 6. So that would be add together. So that would be negative 1 and negative 5. So that means my critical numbers are at 1 and at 5. Got to test them. So I'm going to do a number line, put 1 and 5 there. Plug a value for each section into the first derivative equation and see whether you get out a positive or a negative. You should be looking at positive, negative, positive. So now I know I increase from 0 to 1 in union with 5 to infinity. Sorry, I said 0 to 1. I have no idea why I just said that. I increase from negative infinity to 1 in union with 5 to infinity. And I decrease from 1 to 5. I have a local max at 1 comma something. To get my something, I plug 1 back into the original f of x equation. I have a local min at 5 comma something. To find that something, I plug it into the original equation. Okay, so it's 1 comma 2 and 5 comma negative 30. Now I'm going to test for possible points of inflection. To do that, I look at my second derivative and say, when does my second derivative equal 0 or non-existent? And so that would be at 3. So I plot a number line at 3, test both sides, test something less than 3, something greater than 3. I'm testing by plugging it into the second derivative right now. I get negative and positive, which means I concave down from negative infinity to 3 and concave up from 3 to infinity. And it means I have a point of inflection at 3 comma something. To get that something, I'm going back to the original equation, plugging in 3 and getting out my y value. And so I have an inflection point at 3 comma negative 14. Okay. All right. So that's it for our 2-day lesson. You've got lots of homework to work through and lots of questions to ask. Remember, I'm only an email away. Make sure you're getting your questions answered. Okay. That's super, super important to me. Next lesson will be the last lesson in optimization. And we'll deal with taking everything we've just done and then saying, okay, now draw it. Okay, that's what will be our last lesson. All right, See you soon. Bye.